Today we're going to look at chapter 8.7 and look at a rule called L'Hopitals Rule, named for the mathematician that came up with this. So we're going back to limit notation for a little bit. If we take a look at this, we had problems like this in chapter 1. So let's look at the limit as x approaches -1 of 2x squared minus 2 over x plus 1. Now remember, with limits, you're supposed to first think about direct substitution. If you plug in -1 into this function, you get 2 minus 2 is 0, -1 plus 1 is 0. 0 divided by 0 is not guaranteed to be undefined, and it's not guaranteed to be 0, so we have to explore further. And in chapter 1, we simply factored what we could and simplified. If you simplify this rational expression, it becomes not rational anymore. So the x plus 1s can cancel. And then you can try direct substitution again, and you get 2 times -2 is -4. And you can always graph the original function and look at the graph near -1 as you approach -1 and kind of confirm, is the y value that I'm approaching, is it equal to -4? We also had problems involving infinity. So if we look at the limit as x approaches infinity of 3x squared minus 1 over 2x squared plus 1, we don't really think about this anymore. We just say, oh, this is a rational function. Let's look at its horizontal asymptote. It's 3 over 2. But technically, direct substitution would tell me it's infinity over infinity. So exploring further, again, we haven't done this in a long time because we know to just look for a horizontal asymptote. But we could say, let's divide everything by x squared. And if you do that, you get 3 minus 1 over infinity. Well, 1 over infinity is practically 0. So 3 minus 0 over 2 plus 0 is 3 over 2. We also tried to, if we started with something complex that didn't allow for direct substitution, we tried to clear fractions. We also rationalized a numerator if we had a binomial with a radical in it. So there are lots of kind of tricks and techniques, and we can still do that. But there's also a rule called L'Hopitals Rule that helps in instances where you can't necessarily just work on it algebraically to get the limit to work. So these first two examples are called indeterminate forms. And I think it's indeterminate, not int. But anyway, indeterminate forms. We have 0 over 0 and infinity over infinity. Those are the most common. But we have a few more. Infinity times 0 is not guaranteed to be 0. Infinity minus infinity, not guaranteed to be 0. 1 to the infinity seems weird that that's not just 1, but again, not guaranteed. 0 to the 0, and infinity to the 0. Now there are 1, 2, 3, 4, 5, 6. There are 7 indeterminate forms, and I think in our homework it asks for like 6 of them. So anyway, the most common ones are these two and these two. Those are the most common 4. It doesn't mean you're not going to see the other ones. So when we get an indeterminate form, we either need to try to work on the expression that we're taking the limit of algebraically, or we can use L'Hopitals Rule. Also, I've linked a video, or I will link a video into our Schoology page that explains more about these indeterminate forms. Like, why isn't 1 to the infinity just always 1? So we will, if you're interested in that, it's like a 13-minute video or something, kind of cool. Okay, so what is L'Hopitals Rule? Assuming that f and g are differentiable, so we can take their derivatives on an open interval, except maybe at c, then the limit of, as x approaches c, of f of x over g of x is indeterminate if it comes out to 0 over 0 or infinity over infinity. Then we can say the limit as x approaches c of f of x over g of x, if that's indeterminate and I need to do something with it, maybe I can't work on it algebraically to make it work, I can say that's equal to the limit as x approaches c of f prime of x over g prime of x. Now, I'm not taking the time to prove this in class, but again, I found another good video, maybe this is the 13-minute one, I found another video explaining like why does L'Hopital's rule work. So it's kind of cool. And again, if you're interested in that, it would be worth your time to check it out. So this also works for the limit as x approaches like positive or negative infinity, or just any c value, basically. So c can be anything. There's one thing that's a little bit different, and these notes were created before the AP, the College Board, kind of made this distinction with how they're going to grade. So I didn't leave as much room as I probably would if I had to write this rule out. It used to be that we could just show that, don't write this down yet. It used to be that we could just show, hey, I'm going to get 0 over 0, use L'Hopital's, and maybe we would abbreviate like that, and then we would go into equals the limit of and take derivatives. That was really nice, but technically saying something that is equal to 0 over 0 isn't actually correct. They want us to be more formal than that. So up above, I'm going to write something that we must show if it's a free response L'Hopital's problem. Instead of saying that something is equal to 0 over 0, more formally, you would have to show that the limit as x approaches c of f of x, whatever that is, that equation, is equal to, let's just say it's equal to 0. It could be infinity, it could be negative infinity, but let's just say it's equal to 0. And also that's equal to the limit as x approaches c of g of x. So this is a more formal way than just saying equals 0 over 0. It's showing you, hey, the limit of the numerator equals 0 and the limit of the denominator equals 0. So therefore, we're going to, I think I kept writing on my homework, use L'Hopital's rule. You could also say L'Hopital's rule is needed. I don't know. I just say use L'Hopital's rule. And then you would go on and say, the limit as x approaches c of f of x over g of x equals the limit of, so I'm going to show you the work, but your next step would be to go ahead and actually take derivatives and use the rule. Also, let's make one more note. Sorry, all these little extra notes. L'Hopital's rule, LH, works if you have f of x over g of x. Sometimes I'll get students that want to use it no matter what from here on out. Like if you have a product of two things, it only works if you have a rational expression here. For now, for these two indeterminate scenarios. Okay, finally, let's do a problem. So let's show our formality up here. Let's say the limit as x approaches 0 of e to the 2x minus 1 equals 0. Let's just double check that that's true. E to the 0 is 1, minus 1 is 0, okay? And that equals the limit as x approaches 0 of x, that's the denominator, that definitely equals 0. So we know this to be true. So I'm going to say, now I'm going to abbreviate this in my notes, use LH. And I'm fine if you abbreviate it like that on our homework, but on the AP test, please write out using L'Hopital's rule or use L'Hopital's rule or by L'Hopital's rule, whatever. Okay, how do I use this L'Hopital's rule? What I'm saying is the limit as x approaches 0 of e to the 2x minus 1 over x is equal to the limit as x approaches 0 of what's the derivative of e to the 2x minus 1? It's 2 e to the 2x by chain rule over what's the derivative of x? 1. Once you use L'Hopital's rule once, you take a derivative of the top and the bottom of the fraction, try direct substitution again. Now if you plug in 0, you get 2 times e to the 0 divided by 1. That's just 2 times 1, so that's just equal to 2. As long as you can use direct substitution and not get the indeterminate form again, 0 over 0, infinity over infinity, then you're finished. If this would have still come out to 0 over 0, I would show my limit notation again, use L'Hopital's rule again, and until I get there, basically. Okay, let's look at the next one. We have a rational, and if we plug in infinity, in my head, I'm thinking ln of infinity is infinity, plug that in for x. So then I'm going to write it down formally. the limit as x approaches infinity of ln of x, that equals infinity. And that also equals the limit, infinity equals the limit as x approaches infinity of x. So let's use L'Hopital's. So this limit here, by L'Hopital's rule, can be written as equal to x, the limit as x approaches infinity of the derivative of ln x is 1 over x. The derivative of x is 1. Try direct substitution again. 1 divided by infinity, divided by 1, is very, very small, practically 0. So this limit is equal to 0. Again, you can check all of your answers. I don't want to make my video too long, but I could plug in, we'll do this for one of them. I can plug in ln x divided by x, and take a look at this graph. I can kind of see here, or maybe in the table better yet. Oh, so in the table I'm out at 99 for some reason. You can see we're getting closer and closer to 0 without actually hitting it. Not sure how far out the table will actually let me go. Here we go, even closer to 0 if we're out in the thousands. So you can confirm all of your results by looking at the graph in the table. All right, now number 3, this is one that we had in chapter 1, and we had to use a trick. Remember, the limit as x approaches 0 of the sine of u over u, we'll call it now that we've talked about u sub. The angle here, 2x, needs to match the denominator. If I want a 2 right here, I need to multiply a 2 up here. And so really, this piece, the limit as x approaches 0 of sine 2x over 2x, that's 1. So this is 2 times 1, which is equal to 2. You don't have to use L'Hopital's every single time. But if you wanted to, hopefully you can see that this would be, when I take derivatives, I'm going to get, what, 2 cosine of 2x over 1. 2 cosine of 2x when you plug in 0 will come out to 2. So again, in interest of time, since I could use my chapter 1, I'm going to write chapter 1 right there. Since I could use my chapter 1 method on that one, I will, just to remind you that it exists. Okay. Next one, we're plugging in negative infinity. So if we look at this, infinity over infinity is indeterminate. I know this is going to come out to 0 because there's this idea of function races where exponentials, they grow a lot faster than polynomials. Even if this were x to the 1000th power or whatever, eventually, as you get further out toward infinity, the e to the x is going to grow faster. I know it's an e to the negative x, but we're plugging in a negative infinity, so it's going to work out. But I have to show that. I can't just be like, I was taught to think of that as like function races. E to the x beats x squared. Since we can't cite function races on our AP test, when you plug in negative infinity and square it, you will get positive infinity. And when you raise e to the negative x, plugging in negative infinity, you're going to get e to the positive infinity. So I'm writing that that limit equals infinity. And that's x, limit as x approaches negative infinity of e to the negative x. Since that's true, I'm going to use L'Hopital's. So using L'Hopital's, I would get the limit as x approaches negative infinity of the derivative of x squared is 2x. Derivative of e to the negative x is negative e to the negative x. Oh, and the reason I'm not simplifying that, like, why didn't I just bring this e to the negative x up here and make it x squared e to the x? Because you would get, let's see, infinity squared times infinity, and our answer is not going to work out to be infinity. Also, I can't use L'Hopital's if it's x squared times e to the x. It has to be rational. Okay, let's see. Can we plug in infinity? Technically, no, because we get infinity over infinity again, so I need to show that again. The limit as x approaches negative infinity of 2x. Now that would equal negative infinity. But so would this. The limit as x approaches negative infinity of negative e to the negative x, it will be negative infinity. So use L'Hopital's again. All right, then that is equal to the derivative of 2x. So the limit as x approaches negative infinity of 2 over, this gets back to e to the negative x. Try direct substitution again. Well, this is good because we get 2 over, when you're plugging negative infinity into negative x, you get e to the infinity. 2 divided by a huge number is practically 0. All right, so that one required 2 rounds of L'Hopital's rule. Number 5 is not written as a rational. So the first thing I should do is look at it, actually, to save room here, the first thing I should do is get rid of that and send it to the denominator since it had a negative exponent. Now, if I plug in infinity, I get infinity over infinity. So the limit, so I need to show that formally. The limit as x approaches infinity of square root of x equals infinity. And that's also equal to the limit as x approaches infinity of e to the x. So I'm going to use L'Hopital's. That means that this limit is equal to the limit as x approaches infinity of the derivative of the square root of x is 1 over 2 square root x. Derivative of e to the x is e to the x. All right, and maybe we should clean that up before we try direct substitution. All right, so I'm getting, I guess you don't have to, but I'm going to write it like this. If I plug infinity into this, I get 1 over infinity, which is practically 0. I could have done that back here. Plug in infinity, you get 0 over infinity. 0 divided by infinity is not indeterminate. That is equal to 0. All right, what about this one? This is sort of in a rational form, but it's best to have it as one single fraction. So if you have an x and a square root x up here, your common denominator, I guess it could be x or it could be square root x. Let's just try to make it x. So we could multiply this by radical x over radical x. All right, so we're looking at the limit as x approaches 0 just from the right of, let's see, this stays the same, 1 minus square root x all over x. Now, can we plug 0 into that? We get 1 minus 0 is 1, divided by 0 from the right. 1 divided by 0, that's not indeterminate. We're saying 1 divided by a number that's just to the right of 0. So that means that we would have a really positive infinity. If you try doing L'Hopital's rule with this, like if you look at this, putting in 0, it would have been infinity minus infinity, which is indeterminate. If you jump right into L'Hopital's, I think that you would have a lot more work to do. Like if you would have made this x to the 1.5, then I think you would have had, what, 0 over 0, because you'd have x's everywhere. So you'd have 0 over 0, and then you would have had to do L'Hopital's. So if you take a minute to think about what the best method is to work on this algebraically, this is basically back to a chapter 1. I didn't have to use L'Hopital's. So all of those examples were examples of mostly 0 over 0, infinity over infinity. The last one could have been infinity minus infinity had I not worked on it right away. And a 0 times infinity, we could have done that with number 5. But again, I manipulated it right away. To investigate a 0 to the 0 or 1 to the infinity or an infinity to the 0, so where all of your variables are bases and your exponents have variables in them too, we need a different trick. And it's often used with L'Hopital's rule. So there are steps And it involves logs, which is exciting. So anytime you see this craziness going on, variable is the base and variable in the exponent, just know that this is another version of L'Hopital's. So I just got done saying it needs to be a rational expression, but that's just for these two indeterminate forms. If it looks like this, we're going to be using L'Hopital's as well. I'm going to write the steps as I do them. The first thing to do is make the problem y equals. By the way, let's go ahead and plug in the number. Plug in 1, you get 1 to the 1 divided by 0. You get 1 to the infinity, which is indeterminate. I'm going to need to Google that. Every time I do this, I'm like, wait, is it net or nint? We have it written both ways in the notes, so I'll look that up. Anyway, make this y equals. Y equals the limit as x approaches 1 of x to the 1 over x. I'm making it y equals because I need an equation for which I can manipulate both sides. And remember, limits are asking you what is the y value as we approach this x value. So now eventually you'll combine steps 1 and 2. But once you make it y equals, then you're going to natural log both sides. We natural log because we know derivatives of natural logs and we don't have different derivative rules for logs of other bases. Okay, so natural log y equals, keep your limit notation out in front, natural log x to the 1 over 1 minus x. The reason we're natural logging both sides is because we would like to get this exponent with a variable out of its exponent position. So step number 3 is to use log properties. The log property I want to use is just on the right side here, where I can say if I have the natural log of something with an exponent, that exponent can be pulled out in front and multiplied. So we have natural log of y equals, remember not to drop your limit notation until you actually sub in 1. So now that equals, if you pull a 1 over 1 minus x out in front, you're going to have a natural log of x in the top, and you're going to have a 1 minus x in the bottom. So if you'd like one more step for your notes, let's put that up here. So we said we said 1 over 1 minus x times natural log x, and then I just jumped down here. The reason I don't want to keep it like this is because I want it to look nice and rational so that I can try direct substitution before I get too far, and then use L'Hopital's rule if needed. So try direct substitution at this point. Natural log of 1 is 0, and 1 minus 1 is 0, so this is indeterminate. We can't just write equals 0 over 0 now. We have to write the limit as x approaches 1 of natural log x equals 0, and so does the limit as x approaches 1 of 1 minus x. So use L'Hopital's. Now the left side of the equation stays natural log y, but when I use L'Hopital's rule, on the right side I take the derivative of natural log x, that's 1 over x. I take the derivative of 1 minus x, negative 1, and I try direct substitution again. So 1 over 1 divided by negative 1 is negative 1. So now we have it to, get this up here, we have it to natural log of y. Actually, I don't need to drag that all the way up here, do I? We have that as natural log of y now just equals negative 1. My limit notation is gone because I used direct substitution and got an actual numerical answer. I don't want to solve for natural log of y, I want to solve for y. So I base e both sides. Oh, sorry. Step 4, L'Hopital's. Step 5, base e, solve for y. Okay, so anyway, so that means that y equals e to the negative 1, or 1 over e. You can double check your work on this too, especially for homework. So you can type in to y equals, let me just do it. You can type in x to the 1 over 1 minus x. And then once you get your answer, I would type that in. So like e to the negative 1, and we'll go back to Zoom 6 here. we were approaching 1, so maybe I zoom in a little bit on 1. I like that little zoom box method. It's kind of slow on my computer though. Okay, zoom in there. So as we approach 1, the y value, this is the 1 over x, the 1 over e to the negative 1 line. So yeah, those y values are approaching that value of 1 over e. So you can kind of confirm that way too. So even though this looks kind of complicated, it is the same thing over and over and over. So let's apply that process to this problem. So first check it, make sure it actually is indeterminate. And we don't have to do that formally unless we're using, like I didn't do it formally here because I wasn't using L'Hopital's right away. I only do the formal stuff when I actually am going to use L'Hopital's rule and take derivatives. Okay, so if we plug in infinity, 1 plus a divided by infinity is pretty much 1. And you're raising that to the b times infinity power. So that's b to the infinity, so that's indeterminate. Okay, and I'm going to combine steps 1 and 2. 1 and 2. That's make it y equals, and then also natural log both sides. All right, so instead of y equals, and then on a separate line, natural log of y equals, let's just go ahead and do, it would have been y equals, and then I'll natural log both sides. So natural log of y equals x, the limit as x approaches infinity of the natural log of 1 plus a over x to the bx. And then the next step is to use log properties. Right, so log properties says pull that b to the x down here. Now this one's kind of tricky because pulling that exponent out doesn't give me a rational expression. I'm going to write it on this line. I have bx times natural log of 1 plus a over x. So traditionally your natural log x will stay in the numerator, and it's the bx that needs to become a denominator. So instead of multiplying by bx, I can say this is the natural log of 1 plus a over x bx divided by the reciprocal of bx, 1 over bx. That's going to be important. I'm sorry. There's no bx here anymore. That's going to be important for things to cancel out when we take derivatives. All right, now at this point, let's look at plugging in infinity again. If you plug in infinity, you get the natural log of 1 plus 0, so 0, divided by 1 over infinity, so 0. So we need to show that that's happening. The limit as x approaches infinity of the natural log of 1 plus a over x. That equals 0, and so does the limit as x approaches infinity of 1 over bx. All right, so we have, so we're going to use L'Hopital's. All right, so natural log of y equals the limit as x approaches infinity. The derivative of natural log of 1 plus a over x is 1 over 1 plus a over x times the chain rule, the derivative of 1 plus a over x. So basically the derivative of this term is what? Negative a over x squared? Yes? All right, and then we have, where are we? The derivative of 1 over bx is negative 1 over bx squared. Before we try direct substitution, let's clean this up a bit. So the natural log of y equals the limit as x approaches infinity. So let's see what's happening here. If this is easier to look at this way, you've got a bx squared over negative 1 you could be multiplying up here. So the negatives cancel, the x squareds cancel. So you really just have AB over 1 plus A over x. So all of that ugliness does simplify quite a bit. And then can I take the limit at infinity? So you would get AB over 1 plus 0. So yeah, that limit equals AB. If the natural log of y equals AB, then y equals e to the AB. Can't quite check that one because I didn't have an A and a B, but you could make up A's and B's and plug them in and see what happens. But I'm not going to do that right now. All right, for the next one, let's do something similar. So make it y equals, and then natural log of y equals the limit as x approaches 0. If you want to get really bold, you can remember that, oh yeah, I'm going to take the natural log, then I'm going to pull the exponent out in front. So why don't we do kind of combine steps 1, 2, and 3. That would make it the natural log of 1 plus ax. When you pull this out in front, there's a b in front of that, and the denominator would be x. That makes it so it's nice and rational already. Plugging in 0, you're going to get b times natural log of 1 over 0. So formally, the limit as x approaches 0 of b natural log of 1 plus ax, that equals 0. And so does this silly little limit as x approaches 0 of x. So we need to use L'Hopital's. That means that the natural log of y is equal to the limit as x approaches 0 of the derivative of b times natural log of 1 plus ax. So b over 1 plus ax times the derivative of 1 plus ax. That one's not quite so ugly, is it? That's just a, divided by the derivative of x, which is 1. I'm not going to rewrite this simplified. I have ab or ba, whatever, ab over 1 plus 0. So I can do direct substitution to say that's ab divided by 1. So again, if natural log of y equals ab, then y equals e to the ab. Now these last two problems kind of looked like those compound interest formulas to me, right? Like 1 plus some number over something raised to the bx power. Like that reminds me of that compound interest problem, and it turned out to be e to the ab, where a and b were the numerator and the number in the exponent. Same thing here. A and b were the number attached to the x and the exponent in here, e to the ab. So on these, they would be showing up in multiple choice problems, most likely, on the AP test. You can save yourself a lot of time doing it the long way in multiple choice if you can just say, oh, I know that's e to the ab, and I know this one's e to the ab. The only time you have to be careful is like sometimes b will be a fraction, like it'll be 1 plus a over x to the x over 2. Your answer is still e to the ab, but just keep in mind that b is 1/2. So anyway, these are two good ones to memorize, and then just have no work to do, just blink and be done on a multiple choice. If it's free response, I'd probably go through all the steps and show it still. But again, they're usually multiple choice. All right, there are some practice problems to do. I'm going to assign this for part of the homework, so I'm not going to go through these at this moment. But perhaps in a separate video, if you want it, we'll see what we say in class. There may be a separate video finishing this up. But work on these, and then check my answer key. Check my answer key in the notes tonight, and then we'll come back tomorrow in class and go over them. That's it for today.